today's speaker, Professor Andrei Smilga, and he will speak about non-commutative quantum systems related to Lie algebras. Andrei, you are welcome.
Okay, thank you very much. Thank you for inviting me. I am probably not quite a habitual speaker for this seminar because I'm not a mathematician. I'm a physicist, but physics is the science about nature. And right now, there are not much experimental data, at least in the high energy physics where I'm an expert. And so many of us, many theorists are doing actually mathematical stuff, because if it has no relationship to some processes in nature, then by definition, it's not physics, it's mathematics. But we are doing that using, the language that we learned, and the approach is different. So there is, unfortunately, the difference of languages. And that's why, please, ask me as many questions as possible, more so that, the paper I'm going to report about is not so long. There are not a lot of material, and so I would like probably to discuss profoundly during the talk. It's not necessary, not at all, to postpone the discussion until the end of my talk. So it's about non-commutative systems. For mathematicians, of course, non-commutativity is associated with non-commutative geometry, right? So you have in ordinary space some coordinates which are just numbers and which commute. And what happens if they don't commute? That's the question mathematicians usually pose. But what is physical interest of this construction? Well, people are mostly interested in what is called non-commutative field theory. Field theory is, it's mechanics, or if quantum field theory is quantum mechanics involving an infinite continuum number of variables, which are fields, right? And these fields depend on the position in the space. And people pose questions: what happens if the points of the space on which the fields depend don't commute? Then one obtains some field theory which is non-local, basically, because there is no sharp notion of particular point, so it's a non-local field theory. And that's what I'm not going to talk about. It's not the subject of my talk. There was a good review, I think, about 20 years ago, written by Douglas and Nekrasov. And so I invite those who are interested to read this review. I will talk about something which is much more simple. I will talk about non-commutative quantum mechanics. So quantum mechanics is a system with finite number of degrees of freedom, right? And everybody knows, for example, hydrogen atom, where the dynamical variables are just the coordinates of the electron, right? And so what happens if these dynamical variables, coordinates of electron or something else, don't commute? That's the question which I'm going to explore. And the main, people studied non-commutative field theories and also non-commutative quantum mechanics, starting, for 20 years already, right? That's the first pioneer papers on this subject. Now, the statement which I want to make is that actually non-commutative quantum mechanics doesn't give you anything essentially new. It's just an ordinary quantum mechanics, but in disguise. So you can, there is a way to treat the systems as the system of ordinary quantum mechanics. Then I will give some examples of that, well, associated with the algebra. I will define it very soon. But let me consider the simplest example. Simplest example, yes, and what else I'm going to talk about. So, however, this approach from non-commutative side allows one to obtain some results which I find amusing about the metric of group manifolds. So there are some new formulas. I know that mathematicians nowadays, they don't like so much formulas. They prefer some, well, logical constructions. But, I like the formulas, and that's what I want to present to you. So, the simplest non-commutative system, it has only two variables. So two coordinates, if you want, or two variables, x and y. And suppose that x and y don't commute, and the commutator is not real number.
Hey, Andrei, I'm sorry. Do you show us something on your screen, or it is dead?
I think I show something on the screen. No.
No. Well, at least I see.
Sorry. 1 moment. Reprendre le partage. Okay.
Now it's okay. Thanks.
Okay, so sorry. Now that's what I already talked about. That's the original papers devoted to non-commutative quantum mechanics. And that's the main statement which I want to make, and I want to convince you that it's true. And then, as a byproduct of the study, I will show you some formulas for the metrics of group manifolds and of the spheres. So the formulas are not so complicated, but I haven't seen them in the literature before. And now the simplest non-commutative system, right? So there are just two coordinates, x and y. The commutator is, suppose it's just a number. And if you want to keep x and y Hermitian, so x and y are going to be now operators. They are not numbers, but they are operators. And if you want to keep the hermiticity, then the commutator should be an imaginary number. Now, the algebra involves x and y and also the derivatives. And the derivatives here, commute with the variables in an ordinary way. They commute between themselves, and the commutator of derivative with respect to x is 1, to y it's 0, and so on. Now, that's, non-commutative Hilbert space, if you want, the set of operators, and one can consider some Hamiltonians there to solve spectrum problems. And the basic idea is that it's convenient to replace. So you see, so x and y are coordinates and derivatives are canonical momenta, right? So it's convenient just to replace coordinates and momenta and go over into the momentum representation. And for this system, you just, instead of the momentum, which was the derivative with respect to x and y, you just say that it's new coordinates, a large x. So small x were original coordinates which don't commute. And large x form a momenta, but now they're coordinates and they commute. As far as x, the former coordinate, is concerned, it's an operator, differential operator. So basically, it's just the operator of velocity of a particle. Because this problem just maps to the problem of motion of a particle, charged particle on the plane in a homogeneous magnetic field directed orthogonally to the plane, right? So that's, if you want, a representation of this algebra, right? That's the algebra, not quite Heisenberg algebra, but deformed Heisenberg algebra. And that's a representation. You represent the momenta as just numbers, and the coordinates as differential operators written here. If theta is equal to 0, magnetic field is equal to 0, then it's just ordinary momenta. Momenta with respect to large x. And if theta is not equal to 0, that's actually a physical sense of this quantity is velocity. So that's the idea. This idea will be applied to more complicated systems, which I did will be later.
Andrei, but at this point, it is just one-to-one magnetic field, right? So,
Yes,
why you would not mention this?
Sure. It's just the motion. This problem is the motion of a charged particle in magnetic field. But originally, that was some non-commutative space, and I say that not necessary to think in this non-commutative terms for the space. You go to the momentum representation, and that's it. That's magnetic field. Now the Hamiltonian, that's your choice, how you choose the Hamiltonian. And the natural choice of the Hamiltonian, just the square of the velocity, kinetic energy, right? That's physical interpretation. And so that's what I write. It describes the motion in a homogeneous magnetic field. Theta is just magnetic field. Now, if you have many coordinates which commute with some antisymmetric matrix theta AB, which is constant, then that's the algebra now. That's a little bit more complicated. It involves several x and several derivatives. But again, you go over into the momentum representation, and so you obtain an ordinary Hamiltonian. And now, so this example is well known. It's just to warm up. And now something which is also actually known, but not so well, right? So let you have some Lie algebra realized like that. So X can be interpreted as just generators of some Lie group, right? And F, A, B, C, structure constants of this Lie algebra. Now, in contrast to what we had before, it's just impossible to define the derivatives in an ordinary way, because if you do so, Jacobian identities will not be fulfilled. And that's not a kosher algebra, right? So you should do something else. And people, understood what one has to do in this case. And so the first paper that was 15 years ago, and probably then there were several other papers devoted to that. So instead of the usual derivative, introduce this tilde derivative, postulate that different tilde derivatives commute, and postulate the commutator of this tilde derivative with the coordinate such that the Jacobi identities still hold, right? And so that's the commutator. And unfortunately, I haven't written here what is f, right? I have to write it on the paper and show it to you. Probably I will write it in. So that's the matrix, right? Do you see it? So this matrix F is just the structure constant. It's antisymmetric matrix, so it's structure constant multiplied by the vector of the derivative, right? Of partial derivative. There's the definition of F. So there's the definition of F. And so here you have, well, it's matrix F, right? And so you have some function of this matrix, which is also a matrix. And so that's the commutative which is postulated. I will explain soon why Jacobi identities are fulfilled, but these people, Durov, Milyanak, Samsarov, and Shkoda, also proven it, but in some completely different way. Well, there is a simple way to prove it, and they proved it, but they were pioneers and they proved it in a complicated way. Anyway, if you expand this function into Taylor series and derivatives, that's what you obtain. And the coefficients of this Taylor expansion are called Bernoulli numbers. That's just the coefficients of Taylor expansion of this function. The first few Bernoulli numbers are the following. So it starts with unity, right? So you just expand it in F and it cancels, you obtain unity. Then B1 plus, why I write plus, because they will also be minus a little bit later. Now, but it's just the notation, Bernoulli numbers, B plus, right? So it's 1/2, then it's 1/6. Then before is minus 1/30th, right? And all the odd Bernoulli numbers starting from 3 are just 0. Only B1 is not 0, it's 1/2. And others are 0. It's just the Taylor expansion of this function, and not a big deal. So if you do so, if the algebra is the following, so this commutator is 0, this commutator is written here, and also there is the commutator of x. This algebra involves how many, for example, for SUN, it involves n squared minus 1 x's and n squared minus 1 derivatives, right? And so this algebra is written, it's kosher algebra. Jacobi identities are fulfilled. Now, I want to use this basic idea which worked well for magnetic field. So I replace the momenta, the derivatives, by just numbers, by coordinates, which commute. They commute this delta tilde commute. And so, well, it's natural to represent them as just usual commuting numbers. And x will be non-trivial operator. And it can be represented as a linear differential operator. Well, and the coefficients are non-trivial functions of these new coordinates, large X. That's the basic idea. There is nothing more. But once you did it, you can, well, obtain some corollaries, well, which are sometimes amusing. Now, let me ask whether everything is...
Andrei, this operator is Hermitian?
What is Hermitian?
Definition of XA.
X is just numbers, real numbers.
No, small x.
Small x, small x, they're Hermitian, yes. The operator D is anti-Hermitian, like derivative, and X is Hermitian, right?
Yeah, right. No, but it means that there is a condition on F, right? Because it's not written in Hermitian form.
F is antisymmetric matrix, and so, I think X is Hermitian. Antisymmetric matrix, and if you, I understand what you mean, if you change the order of the derivative and F due to antisymmetry, so it's okay. Now, so if you define it like that, so that's a little bit unusual, how to say, function. Then one can show that these operators D coincide with the generators of right group rotation. So there is a Lie group associated with this Lie algebra. The elements of the group can be multiplied by another element of the group on the right and on the left. And as it's just the generators of group rotations, they satisfy automatically this condition, which is our original condition of commutation of X. Now, let me ask not only Arkady, but other people, mathematicians in the audience. Is everything clear, and can I continue? Is everything clear? So I suppose that yes, right? Then I continue. Okay, so and why this particular function indeed, well, is a generator of group rotation. There are some generators of our Lie group, TA, they're generators, and the element of the group I want to represent in this way. So with this parameter theta, it's convenient for me. Then that's the element, and I multiply it on the right by some group element which is close to, unity, group unity, because I assume that epsilon is small. Then that's the product of two matrices, but one can represent it as another group element. It's another group element, of course. The product of two groups element is a group element. And so the coordinates X are shifted a little bit. And this shift is exactly given by this formula. How one can derive it? So there is some general formula due to Baker, Campbell, and Hausdorff, the product of two group elements, how not necessarily small group elements, how can it be represented as infinite series of some, can be represented as group element, and the exponent represents some infinite series, right? And here, this particular case, which is simpler than the general one, when this epsilon is small. And then this delta X is, linear function of epsilon. So how, again, so that's not usual, that's not usual, but it's known mathematical fact. But there is also a physical proof. Actually, I think It was first proven by Schwinger and Karplus back in 1948, and then by Feynman in 51. So how to prove it? So suppose you have a Hamiltonian, which is, well, some tree Hamiltonian, as physicists say, some H0, unperturbed Hamiltonian, and there is a perturbation V, which is small. Now, one can form such an exponent of EHT. Here, T is not generated, it's just physical time. And this exponent by physicists is called the evolution operator. No matter how is it called, but by just definition of the exponent, you can represent it in this way. So is the limit, well, when n tends to infinity, of nth power of this matrix, right? Now you are interested in the case when V is small. And so there is some large number of factors, and you should keep V in each such factor. And if you do that, you can write everything which is on the left and everything which is on the right as another exponent. And so, and you should integrate over the time moment where you insert this V, right? And that's the formula which you obtain. Integral over T prime from 0 to T of one exponent V and then another exponent. And there are also higher order terms in V, and so by doing that, you can represent the whole Baker-Campbell-Hausdorff formula. So clear, right? Ask questions if something is not clear, because otherwise I will finish my talk before the time. Anyway, if you integrate, just integrate over T prime, then you obtain an infinite series of, well, some multiple commutators. I've written the first few terms of this series. Now, so U naught is this guy. There's the exponential of an unperturbed Hamiltonian. And then you can compare it with this formula. It's actually the same formula. U is associated with this right-hand side in this relation. And then I represent it as this guy has the sense of the evolution operator with unperturbed Hamiltonian, and that's some function. Well, delta x is the perturbation, and that's some group element which is close to 1. And that's this group element is actually written here, right? That's the factor. Now, finally, one can express epsilon via delta x, and then delta x via epsilon, and that's how you obtain this function and Bernoulli coefficients and everything. Probably I didn't give all the details, but hopefully you understand how it's done, more so that probably it's non-mathematical fact. Now we want to do quantum mechanics, right? To do quantum mechanics, we should define some quantum Hamiltonian. And the natural quantum Hamiltonian is just the sum of all d squared, right? Now, so I already made this permutation. So D is an ordinary differential operator with coefficients which depend on large X form momenta, form derivatives. And so you have just to study the spectrum of this Hamiltonian, study the nature of this Hamiltonian. And the statement is that it's nothing but the Hamiltonian which describes.
Sorry, and D is a first order operator.
D is a first, yes, yes. So this D is a first order operator. That's D, right?
I see. Because yes, I had internet problems, so I didn't see it. Okay, thanks. So just a vector field.
Okay, so D is a first order differential operator, and so the Hamiltonian, which is D squared sum over all A, is second order differential operator, right? Something which is very usual in physics. Now, it turns out, so the classical counterpart of this quantum Hamiltonian is written here. So it's some matrix, and P, J, and Pk are canonical momenta. And that's just Hamiltonian, which describes motion, here classical motion, and that's quantum motion on some manifold with inverse metric tensor, which is G, Jk, right? And what is this manifold? Of course, it's nothing but the group manifold. That's the statement, and I will prove it now. What is this matrix G? It is represented, so D involves this function, right? What I've written before, and it can be interpreted as field bind. So I don't know, should I explain what is field bind? That's something, some basic notion of Riemann geometry. So you have a field bind, which is just a wrapper in tangent space. The coordinates, so there are suppose you have a manifold of dimension D, then in tangent space, you may choose an orthogonal wrapper, which has D vectors, and the coordinates of these vectors are called field binds. And if you multiply these field binds, then you obtain just the metric, but here not usual metric, but inverse metric tensor. Now the classical Lagrangian, which corresponds to this classical Hamiltonian, is this. So just imagine a particle which moves along a manifold. Dots are time derivatives, physical time derivatives. And then this metric is just usual metric. Okay, now my statement is that it's a metric of group manifold. Let me prove it. So here you see here it was inverse metric tensor, and that's the just ordinary metric tensor. It's just the inverse metrics, right? And now, so that's the statement that this metric is just invariant metric on the group manifold. One just should compare it with the canonical metric on the group manifold. And this canonical metric can be expressed in this form. So omega is group element, which we choose in this way. So it's convenient to me to have this factor theta, this deformation parameter of our algebra, right? And so the metric is expressed like that. Here, T are generators in a given representation, no matter what representation. And H is Dynkin index of this representation. So then at the origin, when large X is 0, the metric is just delta HK. So that's why I've chosen this coefficient, such normalization, to make it just flat usual metric near the group unity, right? Okay, so that's invariant metric. Now, invariant metric has, what properties does it have? It has the following properties. So if you multiply omega by any group element, then so you obtain some points. So omega is a point on a group manifold, right? Now, suppose you have another point, close point. You multiply both these points, two close points, right? You multiply both these points on some group element. And then what is the metric? Is the distance between the two close points. And the statement is that the distance between these close points is the same, stays the same after multiplication on a group element. And after you can choose by what you can multiply, and clever choice, you multiply it by omega minus 1 of x. Then here you obtain just group unity, and here you obtain something which is close to group unity. And so the distance between these 2 points is the same as the distance between so epsilon is small, between omega of epsilon and omega of 0, right? And so to find the metric in the vicinity of x, so the vicinity of group unity is just flat, right? And to find in the vicinity of x, you have to, well, to make this group rotation, and you should express epsilon in terms of the difference delta x, right? So what is the distance is some quadratic form of delta x, right? Delta x are differences of coordinates. And so you already know how it's expressed in terms of epsilon. And the only thing you need to know is how epsilon is expressed in terms of x. And that's the formula which I shown you before, how delta x, well, epsilon in terms of delta x, or delta x in terms of epsilon. This I shown you before. And so indeed, this particular, function, which appears also in our differential operator D, makes it, makes the algebra correct. So it's indeed describes the right group rotations. So there's the interpretation. The non-commutative system, original non-commutative system, can be interpreted as usual quantum mechanics with some particular, Hamiltonian, and this Hamiltonian describes the motion on the group manifold. So up to now, I talked about the classical Hamiltonian. The metric, it appears in the classical Hamiltonian, but there is also quantum Hamiltonian, where the derivatives and the functions of x are ordered in some particular way. So it's not quite trivial, right? In D, so these functions are on the left of the derivatives, but when you multiply it, so you have some non-trivial ordering, right? And so my claim is that this particular ordering gives you, invariant Laplacian, what is called Laplace-Beltrami operator on the group manifold. So if you have the square of D, then this Hamiltonian commutes with both left and with right rotations. And so the only operator which commutes with both left and right group rotations is Laplace-Beltrami operator. Laplace-Beltrami operator, I just remind, what is it? Operator. That's the Laplace-Beltrami operator. There is some non-trivial ordering of functions of x and derivatives. G, square root of g, is the determinant of the metric, right?
Andrei, but once you define your Hamiltonian as d hat square, you already did this.
Yes, but I have to show a proof that it's indeed concise with a delta. Well,
Yeah, no, but I mean, no, I mean that in this way it's already quantum Hamiltonian, which you can declare to be Laplacian, right?
Well, I want to show that it has some symmetry properties.
Yeah.
There is some formula, right? It's not trivial, it's not immediately clear that the square of d can be expressed in this way. It's not immediately clear, but you can prove it studying the symmetry properties of this d squared.
But no, but with Filbane, it's just more or less clear. If you are using Filbane formalism, then a relation is clear.
Yes, okay. I don't argue. Well, it's all very simple, but still, let me give a formal proof. Formal proof is the following. So this d squared, it obviously commutes with d, right? D squared commutes with d, and d are the generators of right group rotations. But there are many operators which commute with right group rotations, not only Laplace-Beltrami operator. So this operator obviously commutes with d. But it should also commute with left group rotations. But it commutes with left group rotations because left group rotations and right group rotations commute with each other. And so one can define the generator of left group rotations, which is similar to d, but instead of Bernoulli numbers b plus, you have b minus. So that's d, and that's d prime. That's the generator of right group rotations, and that's the generator of left group rotations. And the only difference is in the coefficient b1. All other coefficients are the same. So b plus 1 is 1 half, and b minus 1 is minus 1 half. That's the only difference. But as we, it came from group, and you know that left group rotations and right group rotations commute. And so these generators, which I showed that they are generators, they must also commute. And so this Hamiltonian d hat squared commutes with both d and d prime. And if so, then it's Laplace-Beltrami operator. Now, what games one can play with that? First of all, for an arbitrary group, these Filbanes represent an infinite series which I don't know how to resum. But for SU2, this series can be resummed for Filbanes. And that's the formula which you obtain for the Filbanes, quite explicit formula. There's cotangent, right? Now, well, that's the whole expression, right? For one Filbine, for inverse Filbine, that's how it looks like. And from that, you can find the metric. And the metric has the following form. That's the metric on SU2, right? SU2 is S3. So it's some particular form of the metric of S3, which I haven't seen before, but actually one can, well, there is a change of coordinates which bring this metric to the known form, right? So this A, that's the formula which I want to show. That's the metric, and that's this function. It's like physicists know, well, it's, well, diffraction of Fraunhofer has this formula, but of course it has nothing to do with diffraction of Fraunhofer. Okay. Now, this formula I learned recently, so I placed the first variant of my paper in the archive, and then got a message from Vladislav Kupriyanov, who said that this formula he already knows. He derived it himself, but without interpretation that it's Filbine metric. So he didn't use, as people mostly didn't use, this interpretation as on ordinary quantum mechanics and ordinary differential operators. So he had this formula for Filbines with the different interpretation. And of course, if you know that they are Filbines, you can multiply them over to find the metric. Now, if then you can play the games with this metric. Well, it's the metric on around free sphere, and so the curvature must be constant, and all the invariants of the curvature must be constant. So it's so, and the particular numerical value of the scalar curvature is expressed by these deformation parameters, 3/2 theta squared, and knowing that the curvature on free sphere is 6, well, scalar curvature 6 divided by the radius of this sphere squared, you can define, you can determine the radius of the sphere. Now that's one representation of these differential operators which satisfy the original algebra, and that's universal representation. It works for any Lie algebra and any for any Lie algebra. But for the algebra SU2, there is alternative representation which is simpler. Then the algebra is just, instead of structure constant, you have just Kronig tensor, epsilon ABC. And then one can write this representation, which is also linear operator, linear differential operator, but it's no longer an infinite series over coordinates. So it just first term in y and the second term in y, and y are some other coordinates on three spheres, on three sphere. With that, again, well, I derived it, and then I learned that quite recently, last year, the same formula was derived by these people, but they didn't interpret it as differential operator on the sphere. Anyway, if you do interpret it as differential operator of the sphere and do everything which I showed you before, that's the metric which you obtain. Very simple expression, but again, I haven't seen this particular choice of coordinates, this particular expression before. Anyway, the conventional, widely known form of the metric on any sphere, including 3 sphere, is conformally flat metric which follows from stereographic projection. That's correct for all spheres, including 3 sphere. And now one can, again, amuse oneself to find the change of coordinates, which, first of all, this metric, simple metric, and more complicated metric, this one, are interrelated by a change of coordinates. And there's the change of coordinates. Just tangent, right? Tangent, it's in French, tangent. Also, one can express y via this coordinate z for the stereographic projection. Now, the amusing fact is the following, that if the argument of tangent is pi over half, right, then tangent is infinity. So that's infinity of y. And that means, and if you look to what point, what set of points, this value x, model, the absolute value of the vector of x equals to, pi over divided by theta, right? So that corresponds to the equator of S3. That means that this parameterization gives you not the whole sphere, but only a half of the sphere, from the pole to the equator. That's called projective space, or the group, also the group manifold, but not SU2, but rather SO3. Okay, now the same formulas. Our starting point was the algebra, right? But once we derive the expression for the metric, the same expression works for all spheres of any dimension. Just because, why is that? Because this stereographic projection metric is obviously valid for any dimension. And if you then make this change of variables, then you obtain these two expressions for the metric written before. Now there are two specific cases, however, where some algebraic, relationship of algebraic connotation of this metric can be shown. One case I already considered, that's S3, but another interesting case is 7th sphere. For 7th sphere, you can define the following algebra, which is not a Lie algebra anymore, but it's nonlinear. Here it's something which you had before, just a function of x, right? But earlier, A and DB, so the commutators was as for the generators of SU2 or SU2 for 3 sphere. But now it's the following structure. So there is the first term which has no epsilon ABC, but the tensor eta ABC. So eta A, B, and C, these indices, they are on seven values, right? And that's nothing but the octonion multiplication tensor. So if you have octonions, the product of two octonions can be expressed in this form. So that's the tensor of the third rank, and that's the tensor of the fourth rank, which is the convolution of epsilon tensor with our eta. Just for those who might have forgotten that, I write this Fanon plot for this octonion multiplication tensor. So what does it mean if you multiply? You just follow the arrow. If you multiply E3 and E4, you obtain E1, but then by cycle, if you multiply E1 and E3, you obtain E4. And so there are the sides of the triangle. There are, well, the heights of triangle. It's, I don't know, equilateral triangle. And there is also this square. So this the circle, not square, circle. The circle also counts. So if you multiply E2 by E4, you obtain E6. If you multiply E6 by E4, you obtain E4. That's what is this tensor. But you see that in this algebra, you have also two other terms, nonlinear terms. One term which is not just D, but D multiplied by some linear function of x, and there is another term D multiplied by quadratic function of x. And again, this algebra was deduced not in this interpretation, but in other interpretation, without, so when x were derivative operators, by Vladislav Kuprianov. So that's all about SUN, well, about simple group models. Simple groups. So I gave the examples for the simple groups, right? And now there is a model, well, worked out by Dmitry Gorevich and Pavel Saponov, where the group was not, was semi-simple, was UN, right? And also, well, the formulas, this metric interpretation gives you some amusing formulas. So they started with the following algebra. So they formulated in some different terms, but it's basically this. You have generators of Ln, which commute in more or less usual way. And there is this tilde derivatives, not quite derivatives, but tilde derivatives, and that's the commutator. So if theta equals 0, then it's usual derivative, but you have an extra term, and you see it's non-trivial. The commutator of d tilde and L gives you this in the second term also d tilde, and the indexes are kind of reshuffled, right? So it's K here and M there. It's like that. And one can show that with this algebra, Jacobi identities are satisfied. Now you can do a variable change to represent this algebra in some compact form. So you do it as usual. You introduce the generators of UN. The generators of UN, well, are the generators of SUN, and also, well, extra generator, which is just unit matrix. It's not just one number, but it's unit matrix divided by some coefficient. So after that, you obtain these compact coordinates, which are XA and extra coordinates tau. It's not time, it's extra coordinate. So you have n squared coordinates. And then if you play the same game and represent this and write the algebra, well, it's not yet the same game, you just write the algebra. That's what follows from this general formula. And that follows from general formula for n equals 2. So it's U2 algebra, right? And you see that here you don't have a series of derivatives. Well, earlier in this commutator of d tilde and x, you have the whole series of derivatives. And here you don't have a series, only the linear term, so it's much simpler. It turns out that the algebra for U2 is in some sense, it is double algebra, I mean. It's not just U2 algebra, it's double algebra. It has 8 generators, not 4 generators, but 8 generators, 3x, tau, and then the derivatives, the d tilde with respect to a and d tilde with respect to tau, right? And so it's simpler than for just for SU2 and for any simple Lie group. Now, once you represented it like that, you see that x and tau, well, can be can be well, they're Hermitian operators. They're operators, not numbers, but just operators. They commute like that. And d tilde are anti-Hermitian operators. So if you multiply by minus I, you obtain the momenta. And well, momenta operators. And then you play the same game. You write quantum mechanics and momentum representation. And then the momenta will be just ordinary numbers. And the coordinates, former coordinates, will be differential operators. And that's these differential operators. Again, they are much simpler than for simple Lie groups. For semi-simple Lie group, they appear to be simpler. Well, so that's just usual numbers. Not actually not correct. Minus I d tilde gives a, so you should multiply it by minus I. The momenta are interpreted as usual real coordinates, right? Now, with these operators, you can find field binds, and you can find the metric, and you find that the metric is the following. Very simple. It's conformal flat metric. There's the classical Hamiltonian, and that's the metric, conformally flat metric. Now, if you calculate Riemann tensor with this metric, you can be convinced that the component, so it's Ricci tensor, not Riemann tensor, but Ricci tensor, right? So you can calculate the all components, and then you can calculate the curvature invariance of this metric. And you find that their constants don't depend on the point, and they're the same as on 3 sphere. So you have 4 coordinates, but the curvatures are the same as on 3 sphere. And that means that our manifold is kind of direct product of 3 sphere and R. Well, it's the group U1 R, non-compact version of group U1. Why it's not a circle? Because you can look at this metric and be convinced that the volume of our manifold is infinite. So it's not a compact manifold. It's a direct product of compact manifold over R. And it's, for me, it's amusing that it has very simple form, and still it turns out to be a product of something which depends only on some other coordinates x. I don't know. Here I don't know, haven't worked out the coordinate change. And some other coordinate along this R factor. But, well, that's the compact form. That's the curvature of this metric. So I'm close to the end of my talk, because only one subject I am going to now consider. So there were no questions. So I will end earlier. The problem was well planned. Now the other subject is what happens for higher n. Not for U2, but for UN, if the algebra is UN. Now, if you take this algebra, UN algebra, and go over into compact notations, then that's what you obtain. That's what you obtain. So it's very similar to what you had in U2 case, with one important distinction. So it's just a coefficient. Well, there was earlier theta over 2, and now theta divided by some other constant. It's not important. But here you had earlier only the structure constant, FABC. And now another tensor, which is pertinent for higher unitary groups, DABC appears. And it appears like that. Basically, what you have here is the trace of the product of 2 or 3 generators. And the trace of the product of 3 generators is IF plus D. And you see that this expression is complex. And as this expression is complex, you cannot interpret anymore. You cannot assume that D, the operator D tilde, is anti-Hermitian, because it doesn't match. Well, anti-Hermitian would give here something, but IFABCD, that's okay, but there is also DABC. And that means that the momentum operator, which is I times D tilde, cannot be, is not Hermitian. So the momentum is not Hermitian anymore. And that means that the Hamiltonian, which you might wish to construct, is also not Hermitian. And as it's not Hermitian, there's also quantum mechanics, but with non-Hermitian Hamiltonian, and I don't dare to, to study, to consider really this Hamiltonian, though it's very fresh. Probably I will look a little bit more at that. Maybe something can be said. But what cannot be done, definitely, one cannot extract a real metric, because the field binds, well, which you obtain from this expression are complex and would be metric. The convolution of this field binds also will be complex, and it makes no sense, complex metric. So one can derive in this way the metric, simple expression for the metric on U2, but one cannot derive a simple expression for the metric on UN, and such an expression is not known. Well, there is a generic expression for SUN for any group, which I shown to you, but that's a kind of infinite series, and closed expression is not known and probably doesn't exist. So, well, that's what I wanted to talk to you about. So thank you.
Thanks a lot. Questions, remarks? Well, I have maybe a foolish question, but please tell me why usual commutative quantum mechanics is not sufficient, and why do we have to extend our theory to a non-commutative case?
Well, it's strange to hear this question from mathematicians. Mathematicians, as far as I understand, they just try to generalize the constructions as far as they can, right? And that's what people did, starting from 20 years ago. They started quantum mechanics where coordinates don't commute. And what I'm saying that, well, one can do that, but it's better to consider these systems as systems in momentum representation, and momenta always commute. That's what I'm saying. And why, I don't know. People try to study every possible corner, every possible construction.
Yeah, that's clear, of course. But does it fit to some physical reasons, not just generalization? Of course, we always try to generalize our constructions, but are there some physical reasons for?
Yes. Okay. Physical reasons, I started with that. People are interested in non-commutative field theories. It's something which I didn't talk about, where the fields depend on the coordinates which don't commute.
They do not commute. Yes, I see.
They're interested. I'm not so much interested in that, but well, actually, I started this problem after I talked to Dmitry Gurevich. He showed me his model. And so then I finally understood that it can be described in this way. And
yes, he had just recently a talk about these results.
Yes. So that's a traditional approach of Dmitry, and that's another approach which I just want to show to you.
Okay, thanks. More questions? Yes.
I don't know. No, I'm trying to comment on this invitation because, I mean, partly related to what you asked, that I think that maybe the point which Andrei did not emphasize, that what he defined, it's not a non-commuting coordinate, because it's non-commuting velocities. And everything, no, because it's operator of the first order, whatever. So in this way, commuting coordinates are still were present in definition of this differential operator, and that's why I believe that Andrei says that it's a normal quantum mechanic in this sense, right? And it started physically from magnetic field, which in this language was kind of a trivial metric, actually, right? I mean, in your case, but it's part of what you said as well. So in this sense, there is a kind of a little bit. For example, in classical motion and magnetic field, it is in the circles, okay? And then, for example, you can discuss such stuff like say coordinate of the center of the circle. So you have a kind of circles which okay, coordinate of this circle of the center of the circle would involve velocities. I mean, of course, I mean, so then you will come to the same. No, I mean, algebra which was discussed, you can call it coordinate, but they are essentially, you know, linear in velocity. So it would be again the same. So in this sense, it's not. It does not look. What I'm trying to say is that it's not like refusing of normal quantum mechanics interpretation of coordinate, just saying that he thought that x is vx, so it's essentially its velocity, right? So and non-commuting velocity in magnetic field, it's an old issue. It's not new one, right? So you see that then it becomes indeed very much interpretational what you are talking about the center of the circles or whatever, but anyway, it's going. It's not refusing refuse of normal coordinates. It's just considering object like velocities. No, okay, maybe.
That's quite correct, Arkady, and that's what I said. But the history of the development of these ideas was the following. First, people just thought about this x as coordinates, non-commuting coordinates, and then they understood what you said, that it maps to the problem of the motion and magnetic field. And what I'm doing, just map.
No, just a moment. But look, when you're saying that it is velocities, you are preserving the notion of coordinates, right? I mean, so your coordinates did not disappear.
They used to be momenta, so it's large.
Right. Yeah, so in this way, it's non-commuting kinetic momenta rather than non-commuting coordinates. What I'm trying to say.
After this interpretation, yes. Well, again, so people first thought about this non-commuting geometry, right? And field theory, and then they thought about quantum mechanics. And then they understood that in this particular example, indeed, that's magnetic field. That's not new result. That you knew that, and people knew that. And what I am doing is just I'm extending this idea to some.
Yeah, I agree. I also would suggest to say that what you are doing is indeed like extension of this notion of motion in magnetic field, right? For more complicated stuff.
Yeah.
If you want, yes. If you like, you are right. Yeah.
Okay, thanks. More remarks? No more questions? Well, Andrei, thanks a lot. It was, well, for me, it was interesting.
Okay, so, well, if I'm at your service. Okay, thank you.
Yes, you're always welcome. Just if you want to tell us something new, we will be glad to listen. Well, thanks a lot. Up to now, we have no program for the future, but if we have something to discuss, you'll be acknowledged. Well, goodbye. Have a nice week.
Okay.
See you later. Bye-bye.
Okay, thank you. Bye, everybody. Bye.